Welcome to the Sleepy Science Channel. Here, we use soothing sleepy bedtime science stories to unveil the tranquil mysteries of the universe for you. Tonight, let's relax our minds and embark on a gentle journey into a world of science and dreams, surrounded by the 430 Hz Earth frequency. Right now, hundreds of galaxy clusters are moving through space at a speed of approximately 3.22 million kilometers per hour, rushing toward something we cannot observe. You might think the observable universe shows us everything. Imagine we are trapped inside a bubble 93 billion light years in diameter. But this bubble is but a drop in the ocean compared to the world outside it. Out there, universes are constantly being born like bubbles every second. Cosmic strings slice through reality like invisible blades. White holes give birth to entire galaxies from pure energy. Hello everyone, I am Yan Xian. That number that might short-circuit your brain is 93 billion. Scientists say this is the span of our observable universe, from one end to the other. Within this 93 billion light-year range, it's filled with stars, galaxies, and cosmic dust. You might think this is all that exists, but that is not the case. What follows is truly bizarre. The universe was born from the Big Bang 13.8 billion years ago. The speed of light is the ultimate speed limit in the physical world. Since the light from those distant celestial bodies has only had 13.8 billion years to reach Earth, how can we observe objects 93 billion light years away? This seems mathematically impossible, but the answer precisely reveals the first clue about what lies beyond our view. The entire universe has been expanding. Imagine a balloon with dots drawn on its surface. When you inflate the balloon, the dots move away from each other, even though they themselves never move across the balloon's surface. The universe operates in exactly the same way 13 billion years ago. When a beam of light set out from a distant galaxy, that galaxy was much closer to us. But during the billions of years, this light traveled across the universe to reach our telescopes. The expansion of space pushed that galaxy further away today. That galaxy is 93 billion light years from Earth, even though its light shows us what it looked like billions of light years away. It is this expansion that created the cosmic bubble we inhabit. Inside this bubble, we can observe about a trillion galaxies. Every star you can see in the night sky, every galaxy photo taken by the Hubble telescope, every distant quasar and nebula resides within this 93 billion light-year sphere. Scientists call this the observable universe because it's all we can observe. Everything else lies behind an impenetrable barrier. This barrier isn't made of matter or energy, but is forged by time itself. Light from regions beyond 93 billion light years simply hasn't had enough time to traverse the expanding space and reach Earth. Some light is still traveling towards Earth right now. The images of galaxies it carries won't be observed by humans until millions of years from now. The mind-boggling reality is this 93 billion light-year bubble is only a small part of the true universe. The true universe is vastly larger than what we can see. It's like standing on a beach looking at the horizon. You can see about 32 kilometers of ocean, but there are vast continents and islands beyond the horizon. The principle of cosmic space is the same. Beyond our cosmic horizon, billions of galaxies continue their ancient dance around black holes. Star-forming regions give birth to new stars. Planets orbit distant stars. There might even be regions of space that follow completely different physical laws. Even more incredible, the universe is still expanding. Every second, those more distant regions are receding from us at speeds faster than light. We can never observe them. They exist in a realm forever beyond our reach. The 93 billion light-year limit isn't a wall, but a window allowing us only a glimpse into the nearest room of the infinite cosmic mansion. What prevents us from seeing the other parts of this mansion might shock you even more. 380 years after the Big Bang, the universe once burst into flames. This wasn't ordinary fire. The entire universe was bathed in intense light, so strong that nothing could escape from it. Every photon was like a marble trapped in an infinite machine, bouncing endlessly between particles of matter. The universe was then as hot and white, with temperatures exceeding 10,000 degrees Celsius, resembling the interior of a star. Free electrons zipped around at incredible speeds, constantly colliding with photons, scattering them in all directions. Light would travel just a few feet before hitting another particle. If you could miraculously survive in this cosmic furnace, you would see nothing but a blinding glare. The universe was completely opaque back then. Then everything changed in an instant as the universe expanded and cooled. The electrons finally slowed down enough to combine with atomic nuclei. For the first time in cosmic history, complete atoms formed. Without free electrons to scatter it, light suddenly broke free and began traveling in straight lines through the universe. This moment of cosmic liberation released a brilliant flash of light in all directions simultaneously. Scientists call this the last scattering surface. Every photon that escaped at that time is still traveling through the universe today, forming the cosmic microwave background radiation, and this ancient fire becomes the impenetrable barrier to our observation, because the cosmic microwave background radiation is the first light that could escape from the early universe. We can detect this radiation coming from all directions in the sky. It acts like a glowing shell, encasing the space 93 billion light-years away. This shell is the observational limit that no telescope can surpass. It's like trying to see through thick fog. The fog blocks your view of distant objects. The cosmic microwave background acts similarly, but it's not made of water vapor. It's made of ancient light radiation produced when atoms first formed. Everything that happened within the first 380,000 years after the Big Bang is forever hidden behind this wall of light and fire. We cannot observe the completely opaque early stages of the universe. We cannot observe the moment of the Big Bang itself. We cannot glimpse the cosmic events that shaped the universe in its first few 100,000 years. But what truly puzzles scientists is a particular property of this ancient barrier. The cosmic microwave background radiation is almost perfectly uniform in all directions. The temperature variations across the entire sky are only fractions of a degree. This uniformity seems impossible, Regions of space that never exchanged heat somehow reached exactly the same temperature. It's like turning on two faucets at opposite ends of a bathtub. The water from each faucet starts at different temperatures, yet eventually the water in the bathtub reaches a perfectly uniform temperature. The early universe was essentially the same. This uniformity proves that something extraordinary must have happened before the wall of light and fire formed, and this event points towards the infinite universe we cannot access. You can count about 9,000 stars in the night sky, the number of galaxies observable with the most powerful telescopes reaches to trillion. Each galaxy contains hundreds of billions of stars. The total number of stars in the observable universe is so vast that even if you started counting from the beginning of the universe until now, you wouldn't finish. Yet, compared to the world beyond our view, this immense collection of matter is almost insignificant. Please consider this carefully. Our observable universe extends 93 billion light-years in every direction, forming a sphere containing all detectable things. Every telescope image you've ever seen, every distant quasar, every galaxy cluster resides within this sphere. Basic geometry tells us this fact has profound implications. If you travel from Earth 93 billion light-years in any direction, you would reach the edge of our observable bubble. From that new position, you could observe another brand new spherical volume of space 93 billion light-years in diameter. Some galaxies in this new observable universe might overlap with those we see from Earth, but vast regions of it would be completely unique. If an alien astronomer were located at the edge of our observable universe, about a trillion of the galaxies they could see would be ones we on Earth could never observe. Move another 93 billion light-years further, and you'd find another trillion different galaxies, and so on, extending infinitely in any direction. You would continuously discover new collections of cosmic matter, distributed infinitely throughout space. By studying the cosmic microwave background, scientists have confirmed that on the largest scales we can measure, the universe appears flat, a flat universe extending beyond our observable horizon. Has a clear implication. It is either infinite in scale or unimaginably larger than the range we can observe. If the universe is infinite, then beyond our view, there exist infinitely many galaxies. This isn't speculation or fantasy. The mathematics of cosmic inflation, combined with observations of the universe's flat geometry, almost certainly lead to this conclusion. Beyond our cosmic horizon, there exist galaxies identical to the Milky Way, orbiting supermassive black holes. There exist planets identical to Earth, orbiting stars similar to our Sun. The physical processes that formed our solar system have been repeated countless times in regions we can never observe, and most peculiar of all, because space itself is expanding, galaxies at the edge of the observable universe are receding from us at near light speeds. Those just beyond the cosmic horizon are receding faster than light. This means no matter how long we wait, no matter how powerful a telescope we build, we can never observe them. Cosmic expansion acts like a one-way mirror. We can detect light from distant galaxies, but we can never send a signal back to them. They exist in a realm causally disconnected from our region of space. Every second, thousands of galaxies are pushed by the expansion of space past the point of no return, vanishing forever beyond our cosmic horizon. Yet some force from beyond the horizon is looking back, pulling our local group of galaxies into the darkness. Galaxy clusters shouldn't all be moving in the same direction. Based on everything we know about cosmic expansion, clusters should spread out uniformly in all directions. Like dots on a balloon, the recession speed of each cluster should depend only on its distance from us. The farther away, the faster it should recede. In 2008, when astronomers began measuring the motions of distant galaxy clusters, they expected to see this, but the actual discovery completely overturned expectations. Hundreds of galaxy clusters were moving at speeds exceeding 3.22 million kilometers per hour towards the same region of the sky. This large-scale migration spanned billions of light years and showed no signs of slowing down. The motion of these clusters was unaffected by cosmic expansion, as if pulled by an invisible rope towards something beyond our view. Alexander Koshlinsky and his team at NASA's Goddard Space Flight Center named this phenomenon dark flow, like dark matter and dark energy. Dark flow remains an unsolved mystery. Unlike the all-directional dispersion caused by cosmic expansion, dark flow pulls matter towards a specific region of the sky between Centaurus and Vela. The truly unsettling thing about dark flow is that researchers calculated that to pull galaxy clusters at such astonishing speeds requires an incredibly powerful gravitational force. No collection of matter within our observable universe could produce such gravity. All the galaxies, galaxy clusters, dark matter, and even supermassive black holes we can detect combined cannot generate enough gravity to drive the dark flow. The source of this cosmic pull must lie beyond the edge of the observable universe. It's like watching leaves drift downstream on a river. You see the leaves moving, but you cannot see the waterfall around the upstream bend that creates the current. Dark flow shows us the cosmic leaves, the motion of galaxy clusters reacting to a gravitational pull we cannot observe. What kind of behemoth could pull galaxy clusters across billions of light years? The most mainstream theory suggests it's related to structures formed during the inflationary period. During inflation, some regions of space expanded faster than light, pushing vast amounts of matter beyond our cosmic horizon. These structures might be unlike anything in our observable universe. They might contain the mass of millions of galaxy clusters, compressed into regions larger than our entire visible universe. They could also be made of exotic matter following different physical laws. Some scientists propose even stranger explanations. Dark flow could be caused by gravitational leakage from a parallel universe. It could also be evidence for cosmic strings, one-dimensional curves in the fabric of space-time that could span the entire multiverse. In recent years, some studies have questioned the reality of dark flow, suggesting the observed motion might be due to measurement errors, but other research teams continue to find evidence for this mysterious cosmic flow. The debate continues, but one thing is certain: if dark flow is real, then beyond our view lurks something of unimaginably large mass, and the same region of the universe might also bear the permanent scars of a collision with the neighboring cosmos. Deep in the cosmic space of the constellation Indus, there lies a bruise. This cosmic wound spans 1.8 billion light-years and appears as a cold spot. In the cosmic microwave background radiation, the matter density in this region is about 100 times lower than normal, as if something pierced reality and scooped out a huge shock of matter from the early universe. Scientists call this the CMB cold spot, and it shouldn't exist. The CMB is the afterglow of the Big Bang, the first light released when the universe became transparent 380,000 years after its birth. This ancient light should have extremely small temperature variations across the sky, but the temperature deficit in the cold spot is so significant, it cannot be due to random chance. It's like throwing a stone into a calm pond. Ripples spread out from the impact point in perfect circles, but if you found an area in the pond where water mysteriously vanished, leaving a dry patch surrounded by normal water, that dry patch would be analogous to the cold spot in the CMB data. The strangest explanation for the cold spot involves bubble universe collisions. According to eternal inflation theory, our universe is a space-time bubble that formed after inflation stopped in our region, while the surrounding multiverse continues to inflate. Other bubbles form nearby. Sometimes two bubbles can collide before their boundaries harden into separate realities. If our universe collided with a neighboring bubble universe, it would leave a temperature anomaly in the CMB, like the one we observe today. The collision would compress matter in some regions and dilute it in others, leaving a permanent scar in the ancient light radiation. Computer simulations of bubble collisions show that if our universe experienced such a hit, we should see circular patterns in the CMB. Research teams analyzed CMB data, trying to find these telltale signs. In 2010, scientists thought they had found 4 circular patterns in the data from NASA's Wilkinson Microwave Anisotropy Probe WMAP that matched the predicted signatures of collisions, but subsequent statistical analysis showed these patterns could just be random fluctuations. More detailed observations from the European Space Agency's Planck satellite also fail to confirm the collision hypothesis. Other explanations for the cold spot include a cosmic void, a region of space extremely devoid of matter. Such voids can create temperature drops in the CMB through the integrated Sachs-Wolf effect. Photons lose energy, climbing out of the gravitational wells of denser regions. Some researchers suggest the cold spot could be evidence of extra dimensions, or a sign that Einstein's general relativity fails on cosmic scales. Others propose it might indicate flaws in our understanding of dark matter and arc energy. The cold spot remains one of the most puzzling features in the CMB map, whether it's the result of a bubble collision, a product of exotic physics, or a signal from an unknown cosmic structure. Its existence proves our understanding of the early universe is still incomplete, and the mystery deepens when you realize that space itself can move faster than the ultimate speed limit. Nothing can travel faster than light, except the fabric of reality, Einstein's special relativity. sets an absolute speed limit for all matter and energy. Objects with mass cannot reach light speed. Massless objects cannot exceed light speed. This cosmic speed limit governs every particle, every force, every wave in the universe, but space itself completely ignores this rule. During the inflationary period, shortly after the Big Bang, space expanded exponentially in less than a second. Parts of the universe expanded by a factor of 1026 or more. This means a region smaller than a proton could inflate to the size of a basketball or larger, and this expansion happened at a speed far exceeding the speed of light over the same distance. Imagine two ants on opposite sides of a deflated balloon. When you rapidly inflate the balloon, the ants move apart. Even though they never move across the balloon's surface, the expansion of space works exactly the same way. Galaxies aren't moving through space faster than light. Space itself is stretching, carrying the galaxies along with it. This distinction allows cosmic expansion to break the light speed limit without violating physical laws. The implications are staggering during inflation. Regions of space that were once close enough to exchange light and heat were suddenly pushed apart to distances light could not cross. This also explains why the CMB is so uniform before inflation began. The entire observable universe was smaller than a grain of sand. Every part of it could interact and reach the same temperature after inflation. These regions became causally disconnected. They could no longer exchange information or influence each other because signals would need to travel faster than light between them. Today, driven by dark energy, cosmic expansion is still accelerating. Galaxy clusters beyond a certain distance recede faster than light. We can still observe some of them because their light was emitted billions of years ago when they were much closer. But the light they emit now will never reach Earth. This creates a cosmic event horizon similar to a black hole's boundary. Information from beyond this horizon can never reach us, no matter how long we wait. Currently, this horizon is about 16 billion light-years away, and it expands outward every second. Inflation not only affects our ability to observe distant objects, but fundamentally shapes the structure of reality. It determines which regions of space can interact and which remain forever isolated, and the inflationary process that created our cosmic bubble is still creating new bubbles in the infinite multiverse. Inflation did not stop everywhere at once. Imagine the early universe as a vast ocean of space-time, expanding exponentially in all directions. Within this cosmic ocean, there was a special inflationary field that drove the expansion by stretching space faster than light for a brief period. This energy field dominated all of reality. Then, in small, randomly distributed regions within this inflating ocean, the inflationary field began to decay. When the inflationary field decayed in our region, inflation stopped. The enormous energy that drove the exponential expansion transformed into matter and radiation. This transformation created a hot, dense plasma that eventually cooled to form atoms, stars, galaxies, and everything we observe today. Our observable universe was born. However, the inflationary field did not decay everywhere simultaneously. In most of the cosmic ocean, inflation continues to this day. These regions keep expanding exponentially, stretching space, diluting matter, and eventually becoming almost empty. And within this backdrop of eternal inflation, new bubbles randomly stop inflating and convert their energy into matter. It's like steam bubbles forming randomly in boiling water. Each bubble is a unique region with properties different from the surrounding liquid. Our universe is one such bubble formed in the eternally boiling cosmic pot. The mathematics of this process is fascinating. Quantum fluctuations in the inflationary field determine when and where bubbles form. These fluctuations are completely random, like radioactive decay. You can calculate the probability of a bubble forming, but you cannot predict precisely when and where each individual bubble will appear. The key point is, once inflation starts, it becomes eternal. The inflationary field creates new space faster than it can decay into matter. Even though countless bubbles form every second, they occupy only an infinitesimal fraction of the total volume of the universe. Most of space remains inflating. This eternal inflation creates a multiverse composed of infinitely many bubble universes. Each bubble experiences its own Big Bang, evolves its own galaxies and stars, and eventually dies when its energy runs out. Meanwhile, the background space continually creates new bubbles. In an endless cycle, our bubble universe now spans about 93 billion light years. Other bubbles might be smaller, larger, or have completely different scales. Some bubbles might have much higher matter density than ours. Others might be almost empty. A few might have evolved with completely different physical laws when they formed. The distance between bubble universes depends on the inflation rate. Relative to the bubble nucleation rate, most bubbles are separated by eternally inflating space and can never communicate or influence each other, but occasionally two bubbles form close enough that their boundaries collide before the intervening space inflates too much. When this happens, the two universes collide, and the effects ripple through both realities. On the smallest scales, reality splits billions of times every second. Zoom in on any seemingly empty patch of space, down to scales smaller than the Planck length, and you'll find the smooth fabric of space-time breaks down into a churning quantum foam. Virtual particles constantly flicker in and out of existence, their lifetimes too short for any clock to measure. This quantum foam doesn't just affect empty space, it drives the birth of entire universes. During the inflationary period after the Big Bang, quantum fluctuations in the inflationary field determine which regions would stop inflating and form bubble universes. These fluctuations are completely random and occur everywhere. In the eternally inflating multiverse, the process is as follows. The inflationary field has a specific energy value. It is this energy that drives the exponential expansion of space. Quantum fluctuations occasionally cause the energy of the inflationary field in small patches of space to be higher or lower than the average. When the inflationary field's energy drops below a certain critical threshold, inflation stops in that region. The energy of the inflationary field transforms into ordinary matter and radiation. These quantum events happen randomly in space, following the laws of probability. In any given patch of inflating space, there is a calculable probability that a fluctuation will trigger bubble formation within a very short time interval. Multiply this probability by the infinite volume of eternally inflating space, and the result is an infinite number of bubbles constantly forming. The math is astounding. Every second, countless quantum fluctuations give rise to new bubble universes in the infinite multiverse. Each bubble experiences its own Big Bang, evolves its own physical laws, and forms its own cosmic structures. Most bubbles are separated by continuously inflating space and never meet. You can compare the quantum foam to cosmic seeds scattered by the wind. Most seeds fall on barren ground and never grow, but occasionally a seed lands on fertile soil and grows into a full ecosystem. Bubbly universes are these cosmic ecosystems that grew from quantum seeds in the inflating multiverse. The implications go far beyond just creating universes. If quantum fluctuations can spawn infinite bubble universes, then every possible combination of physical laws must exist somewhere in the multiverse. In some bubbles, gravity is repulsive, not attractive. In some universes, the electromagnetic force works opposite to ours. In some realities, time flows backward or in multiple directions at once. Some bubbles have physical constants perfectly suited for life. Others become wastelands where stars never form and matter cannot clump together. A few bubbles might have physical properties so strange we cannot even imagine them. The anthropic principle suggests that we observe a universe suitable for life simply because we couldn't exist in the barren ones. Conscious observers like us can only appear in the few bubbles that allow complexity to form. This means in other bubble universes, there might be exact copies of you. They share almost identical histories, or might differ due to different choices or historical paths. Occasionally, adjacent bubbles in the multiverse collide, with far-reaching cosmic consequences. There is an equation that proves infinite universes exist. This simple mathematical formula describes the probability that a given patch of inflating space will form a bubble universe within a specific time period as time approaches infinity. This probability approaches 100% in infinite time and space. Bubble formation is absolutely inevitable. The mathematics of eternal inflation is like a cosmic gamble where the house always loses. Imagine flipping a coin forever. Each flip has a 50% chance of heads. Flip enough times, and you're guaranteed to see heads at least once. If you have infinite coins and can flip for infinite time, you'll see heads infinitely many times. Even though the outcome of each flip is unpredictable, bubble universe formation follows the same principle. Quantum fluctuations constantly flip coins in the inflating multiverse. Each fluctuation has a tiny probability of triggering bubble formation in infinite space and eternal time. Bubble formation is not just inevitable, it's infinite. The key is understanding exponential growth during inflation. The volume of space doubles repeatedly in a very short time, and in regions where inflation hasn't stopped, This doubling continues forever, even if the probability of bubble formation is extremely low. The exponentially growing volume of inflating space ensures that the rate of bubble formation accelerates. It's like bacteria reproducing in a petri dish. Each bacterium has a small probability of dividing within a certain time interval. Initially, division is slow because there are few bacteria. As the number of bacteria increases, so do the chances for division. Eventually, the population explodes exponentially. Eternal inflation works similarly. Every patch of inflating space has a small probability of forming a bubble universe. As inflation creates more space, the number of regions that could form bubbles increases, even if the probability per region remains constant. The total rate of bubble formation increases exponentially. An even more astounding mathematical conclusion comes from Andre Lin's chaotic inflation model. This model shows that when a bubble universe forms, its physical properties are random. The strength of gravity, the mass of the electron, the speed of light, the strength of the electromagnetic force, these fundamental constants are randomly determined as each bubble forms. This randomness ensures an infinite variety of physical laws. In the multiverse, some bubbles have gravity so weak that matter can never clump into galaxies. Some have electromagnetic forces so strong that atomic nuclei tear apart due to charge repulsion, and a few bubbles have physical constants that are just right, allowing for complexity, life, and consciousness. The anthropic principle explains why, among the infinite random possibilities, we observe a universe suitable for life. Conscious observers can only arise in the few bubbles that permit their existence. Mathematical models also predict the frequency of bubble collisions. When two bubbles form close enough in space and time, their expanding boundaries eventually meet and interact. These collisions produce gravitational waves in both bubble universes. The characteristics of these waves depend on the collision angle, the relative speeds of the bubbles, and the differences in their physical properties. Most importantly, these gravitational waves would leave a permanent imprint on the cosmic microwave background of each universe. How can scientists detect evidence of bubble collisions in our universe? If our bubble universe ever collided with a neighboring bubble, the gravitational waves from the impact would travel through our space at light speed and reach the last scattering surface. These collision waves would create specific patterns of temperature anomalies in the CMB. Different from random fluctuations, collisions leave traces as circular rings centered on the collision direction. Their size and intensity depend on the specific collision parameters. Matthew Johnson and his team at the Perimeter Institute for Theoretical Physics used computer simulations to precisely predict the signatures that different types of collisions should leave in the CMB map. They created detailed templates in 2010. Researchers announced they had found for possible collision signatures in the data from NASA's WMAP satellite. Each signature was a set of concentric rings with temperature variations matching theoretical predictions. This discovery suggested our universe might have collided with four different neighboring bubbles. However, subsequent analysis revealed problems with this interpretation. More detailed CMB maps from the European Space Agency's Planck satellite showed that these seemingly collision-related patterns were likely statistical flukes. Random temperature fluctuations can sometimes coincidentally form ring-like patterns. Scientists are still searching for collision signatures using more refined methods. New analysis techniques can distinguish real collision signatures from random patterns by examining multiple statistical properties simultaneously. If conclusive evidence for a bubble collision is found, it would revolutionize our understanding of cosmic reality. This discovery would prove our universe is just part of a vast multiverse, and that other realities exist beyond our cosmic horizon. Collision evidence would also provide our first observational window into studying the physics of the multiverse, allowing us to understand how bubble universes form and interact. Meanwhile, the search for collision traces has revealed an even stranger possibility: the existence of bubble universes with fundamental natural laws, completely different from our own. In some bubble universes, electrons might have masses comparable to protons. Gravity might be repulsive. When each bubble universe forms, it randomly gets its own set of physical laws. Parameters like gravitational strength, fundamental particle masses, the speed of light, electromagnetic strength are randomly chosen from the vast space of possibilities at the moment of bubble nucleation. Most parameter combinations result in barren universes where nothing interesting can happen. Imagine a universe where gravity is 10 times stronger than ours. Cosmic gas would form stars more easily, but these stars would burn through their nuclear fuel in just millions of years. Stellar explosions would be so powerful they would sterilize entire galaxies with radiation. Strong gravity would crush planetary surfaces, preventing complex chemistry. Conversely, in a bubble where gravity is 10,000 times weaker than ours, matter would never clump into stars. Galaxies would exist as thin, cold gas clouds drifting through space. No nuclear fusion, no heavy elements, no planets, and certainly no life. Changes in the electromagnetic force would have equally dramatic effects. If it were slightly stronger, atomic nuclei would be torn apart by charge repulsion. If slightly weaker, electrons would spiral into nuclei, eliminating chemistry entirely. Some bubble universes might evolve completely different particle physics. In these realities, the fundamental building blocks of matter follow alien rules. Particles that attract in our universe might repel there. Forces that weaken with distance here might strengthen with distance there. The strangest possibility is universes with different numbers of spatial dimensions. We live in a three-dimensional space plus one-dimensional time reality. Other bubbles might have 4, 5, 10, or even hundreds of spatial dimensions. Moving in higher dimensional space would be a completely foreign experience. Objects could appear from directions that don't exist from our 3D perspective. A four-dimensional sphere passing through our 3D space would mysteriously appear and disappear. String theory suggests bubble universes with compactified extra dimensions might be common. These extra dimensions are curled up so tightly they appear as points from our 3D view, but they affect the properties of fundamental forces and particles. Some theoretical physicists propose that advanced civilizations in other bubbly universes might have mastered technology to manipulate their local physical laws. By understanding the relationship between space-time geometry and physical laws, these civilizations might be able to alter fundamental constants within limited regions. Such physics manipulation technology might seem like magic to us. They might create regions where gravity flows backward, where time passes at different rates, or where matter transforms according to different rules. The anthropic principle suggests most bubbly universes are barren. Only a tiny fraction of bubbles develop conditions suitable for complexity and consciousness. This means intelligent life is extremely rare and precious in the infinite multiverse. But within our bubbly universe, exotic physics might not only exist far beyond our view, they could also exist within the observable universe as reality warping objects. In some corner of the cosmos, black holes have an evil twin. They don't destroy, but create. Black holes swallow everything that comes near. White holes are the exact opposite. These theoretical objects violently expel matter and energy. Nothing can approach their surface. They are like cosmic geysers, spewing enough material to form galaxies into space. The same mathematical theory that predicts black holes also predicts white holes. Einstein's general relativity describes how massive objects warp space-time. When you solve the general relativity equations for a black hole, you get to solutions. The first solution describes matter falling through the event horizon towards the central singularity. The second solution describes matter erupting outward from an unreachable central point. Black holes correspond to the first solution. White holes correspond to the second. Imagine watching a film of matter falling into a black hole. Now play the film in reverse. In the reversed film, matter erupts from the central point and moves away faster and faster. That's what a white hole might look like. White holes might explain some of the most violent high-energy phenomena in the universe. Gamma ray bursts release more energy in a few seconds than our sun will in its entire 10 billion-year lifetime. Quasars shine with the brightness of 1 trillion stars, concentrated in a region smaller than our solar system. Active galactic nuclei accelerate particles to near light speed and jet them out millions of light years. Current theories suggest these extreme objects are powered by matter falling into supermassive black holes, and falling matter heats up before crossing the event horizon, releasing enormous energy. But some scientists propose white holes might offer an alternative explanation for these cosmic violence events. However, in our universe, white holes are inherently unstable. Any matter near a white hole would block its outward eruption, causing it to immediately collapse into a black hole. This instability might explain why astronomers have never observed a definitive white hole signal. But in other bubbly universes with different physical laws, white holes might be stable and common. These objects could serve as cosmic factories, constantly producing the matter and energy that form galaxies. Some cosmologists propose the Big Bang itself might have been a white hole event. Our entire observable universe might have erupted from a point in a higher dimensional space. This eruption produced all the matter and energy we observe today. This white hole Big Bang model offers an alternative to the standard inflation theory. The most speculative theories suggest black holes in our universe might be connected to white holes in other realities. Matter falling through a black hole's event horizon might erupt from a white hole in another bubble universe. This connection could form cosmic tunnels spanning different regions of the multiverse. Although white holes remain theoretical, other exotic structures definitely existed in the early universe, and they might still be moving through space today. Imagine a crack in reality. It's too thin to observe, yet a cosmic string just 1.6 kilometers long could have more mass than Earth. Cosmic strings might be one-dimensional defects in the fabric of space-time. They formed in the first instance after the Big Bang, when the universe underwent rapid phase transitions, breaking the unified state of the fundamental forces. It's like water freezing. When liquid water cools and crystallizes, cracks sometimes form between different ice crystal regions. These cracks are defects where the crystal structure didn't align perfectly. A similar process happened when the early universe underwent phase transitions separating the forces. Cosmic strings formed at the boundaries between regions with different properties in space. The physical properties of cosmic strings defy everyday experience. Each string is no wider than a proton, yet incredibly dense. A 1.6 kilometers long cosmic string could outweigh Earth. Their gravitational fields are so strong they bend light and warp time. If cosmic strings exist, they are almost indestructible, unlike ordinary matter. Cosmic strings are topological defects. To destroy them, you'd have to fundamentally change the fabric of space-time. They are permanent scars left from the birth of the universe. Cosmic strings could also be incredibly long. The shortest might stretch from one end of the observable universe to the other. Most extend into regions beyond our view. Some might form closed loop smaller than galaxies. Others might connect our bubble universe to neighboring realities. The motion of cosmic strings also produces gravitational waves. When strings vibrate, oscillate, or cross each other, they create ripples in space-time. These ripples can be detected by instruments like LIGO. The signature of these waves differs from those produced by black hole or neutron star collisions. Some scientists believe they might have already detected signals from cosmic strings. The nanograph collaboration measures tiny timing variations in pulsars to detect gravitational waves. Recent data shows patterns that could be consistent with a network of cosmic strings. Cosmic strings might also influence the formation of galaxies and the large-scale structure of the universe. Their immense gravitational fields would attract ordinary matter and dark matter, forming linear concentrations of matter along their paths, seeding galaxy formation. If cosmic strings can connect our bubble universe to other realities, they might provide limited channels for information transfer between different universes. Electromagnetic signals might travel along string networks, carrying information between otherwise causally disconnected bubble universes. Scientists are still searching for cosmic strings using various methods. Gravitational wave detectors, CMB analysis, large-scale structure surveys, all offer different avenues for finding traces of cosmic strings. If cosmic strings are discovered, it would prove that reality contained structures far beyond our imagination, extending into dimensions we are only beginning to understand. Two synchronously rotating black holes might dare a tunnel through the fabric of space-time. This isn't science fiction. Mathematical solutions of Einstein's equations show that under specific conditions, extreme space-time curvature caused by massive objects could form shortcuts connecting distant regions of the universe. Scientists call these wormholes. The technical requirements for constructing a wormhole are extreme. You would need to charge black holes placed at a precise distance. Their charges must be perfectly balanced. Not so attractive they merge, not so repulsive they fly apart. You would also need cosmic strings. These one-dimensional curves of space-time could act like cosmic scaffolding to keep the wormhole tunnel open. Remember, cosmic strings are thinner than a proton, but denser than a neutron star. Their immense tension could theoretically prevent the wormhole from collapsing under its own gravity. The resulting structure would be a stable tunnel connecting to points in spacetime. Enter one end, and you instantly emerge from the other, no matter the distance between them. The travel time through the tunnel would be almost zero. The concept of bubble universes becomes crucial here. If cosmic strings form during inflation, they might span the eternally inflating space, reaching from one bubble universe to another. Wormholes built using these transbubble strings could directly connect different realities. Imagine traveling through such a tunnel into a universe with completely different physical laws. Gravity might be repulsive there. The electromagnetic force might work in reverse. Time might flow at a different rate. The experience would be like walking through a door from one dream into another. Unfortunately, even theoretical wormholes face serious stability issues. The cosmic strings holding them open would gradually lose energy through gravitational wave radiation. As the strings shrink, the wormhole tunnel would collapse. Most models predict wormholes would collapse completely within microseconds, but some theoretical frameworks suggest quantum effects or exotic matter with negative energy might keep wormholes stable for longer. Such stable tunnels might exist naturally in regions of the universe where inflation created the right conditions. Advanced civilizations in other bubble universes might have developed technology to create and maintain artificial wormholes. Such technology would allow them to explore distant regions of their own universe and even visit neighboring bubble realities. If stable wormholes exist, they would solve the problem of cosmic isolation caused by superluminal expansion. Bubble universes that would otherwise be forever separated could remain connected via a wormhole network, enabling communication and travel. The implications are profound. A cosmic internet connecting multiple realities could allow different bubble universes to exchange information, matter, and energy, even if their physical properties differ greatly. Scientists are still searching for wormhole traces in gravitational wave data and CMB observations. Finding evidence for these cosmic tunnels would prove the barriers between realities are not absolute, but some theoretical physicists propose parallel realities might be closer than we think. They might even run backwards in time. For every second our universe moves forward, its mirror twin universe moves backward 1 second. This mirror reality, formed at the same moment as our universe and the Big Bang, both share the same starting point but evolve in opposite time directions. We experience time flowing from past to future. Time in the mirror universe flows from future to past. This concept stems from fundamental symmetries in physics. Most physical laws work equally well whether time flows forward or backward. For example, throw a ball, it falls to the ground. Play this process in reverse, and the ball bounces up from the ground back into your hand. Both sequences follow the laws of gravity and motion, the mathematical equations. Don't prefer either time direction, but the second law of thermodynamics breaks this symmetry. In our universe, disorder entropy always increases over time. Hot coffee cools down. It doesn't heat up. A shattered glass doesn't reassemble itself. Dead organisms don't come back to life. Cosmologists like Sean Carroll have proposed the Big Bang might have created two universes with opposite entropy increasing directions. In our universe, entropy increases in the forward time direction. In the mirror universe, entropy increases in the backward time direction. Think of watching a film of a person's life played in reverse. You'd see them grow younger, forget knowledge, and eventually become a baby. From our perspective, the mirror universe evolves in reverse, but conscious beings in the mirror universe would perceive their own time flow as normal. They would see their universe evolving forward and ours as running backward. This creates a profound symmetry in cosmic evolution. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.